class, welcome to our fifth segment in our online adventure in Chapter 4 with ratio and regression estimation. Last time we hit the theory pretty hard and sort of trying to understand how we might actually use ratio estimation inside of the domain estimation. And we recognize that domains are different than strata in the sense that we often don't know the domain membership beforehand. But if we do know the domain membership beforehand, we can make use of that in the ratio estimation process. And we may or may not want to stratify on every domain variable that we have at our disposal, even if we have them all available at the time we design a study. And that is in part because we may have some primary objectives in the survey where we want to actually project to the entire population, and we may have some secondary objectives where we want to actually get domain-specific estimates. And domains actually can be complicated, like we saw last time with the example where it took us to identify 4 variables, or asking 4 basic survey questions to identify people who were inside our domain of interest. The reason why that example is really important for us to realize is that domains are not just simply defined. They could be simply defined as maybe males or females, or older folks versus everyone else. But in general, they can actually be very complex. The idea is that the more complex the domain definitions are, the likelihood that you'll have very few people in the domain of interest to get a reasonable estimate. Now, that generally more complicated domains are usually asked about when you have very large scale surveys or national surveys or large state surveys like the California Health Interview Survey, which we talked about last time, in order to support domain estimation in a reasonable way. This time I'm going to go through 2 examples. We're going to work the examples by hand, and then in the next segment I'm going to tell you how all of this is done in R, and I'll encourage you to work through some examples. There is going to be an example posted in a mini homework assignment on the coronavirus data, and we're going to look at using a ratio estimator there momentarily. I'm preparing that data now and we'll release it soon, so be on the lookout for that. I realized last time that when we were doing this that there was a little bit of confusion on the notation, so let's clarify the notation a little bit here. So we recognize that our parameter in the domain situation is this y bar ud. Now we break this down. The u refers to the universe or the population. The d refers to the domain of interest. So this is our population parameter, and we define it as the total of the u variable for the population, where the u variable is equal to yi times the indicator of whether or not you're in the sample or in the domain. And the tx is just the sum of all those indicators to denote the number of people in the population or sampling units in the population that actually fall in the domain. So this tu is nothing more than adding up all the y elements that are inside of the domain, and there are capital N D of them. This total for the x variable is simply the size of the domain in the population. We estimate this domain parameter by using what we call y bar d. You'll also see me use y bar hat ud, because this is really giving us homage to the fact that we're using a ratio type estimator for this. This is also equal to b hat in the case where we're looking at domain estimation. Last time when we were working with ratio estimation, we realized that b hat was only the beginning of getting us a mean estimator or a total estimator, or b hat was actually the estimator of a rate. In this case, we're sort of positing domain estimation as a rate. We're trying to figure out what is the total of the y's given the number of people who actually fall in that category in the population. So this is actually why we express it as a rate. It is nothing, you estimate this b hat by u bar, which is the sample average of the u variables in your sample. Remember, the u variables are the yi's times the indicator of whether or not a sampling unit is included in the domain. And then x bar is just basically the average number of, or the proportion of units in the domain that are actually in your sample. So the variance of this estimator is akin to what we saw on the ratio estimators, but because we're using, because x bar actually represents a function of little n sub d, which is the number of elements in your sample that are in the domain, you start to see a bit of simplification in this formula here. And then this s squared yd, it wasn't clear from the notes last time what that quantity really was referring to. So I wanted to clear that up here so that we're all on the same page, so that when we do these calculations, you know exactly what's going on. So this s squared yd is actually equal to the squared difference, right? These deviations of the y elements minus y bar d. Now y bar d, again from upside here, is b hat. So that you can place either one. They're both the same quantity. We just refer to them differently. Now this is I in D. So this is the elements in your sample that fall inside the domain. So I'm summing up. So this, you could effectively write this as, if you took a shortcut, I equals 1 to nd yi minus y bar d quantity squared. But keep in mind, right, that this really implies an order. So the first few yi's wouldn't necessarily be in the domain. So that's why we don't order it in this way. But in general, that's essentially where the number of summands that we're going to have here is effectively only n sub d, little n sub d. And then I'm going to divide this by n sub d minus 1. So if I look at this another way, I could just call this thing out, which we already know what it is. It's the sample variance of the yi's in your sample that belong to the domain of interest. That's it. You gather all the yi's that are in your domain from your sample. You take the sample variance of those things. That's exactly what this is. It's nothing more fancy than that. The notation is a little bit laborious here because we're trying to track domains. But keep in mind that effectively what we're doing, you already know how to do. You've been doing this all semester. So there's nothing new there. It's just a matter of which y's do I take, and it doesn't include the zero out elements. Now, we often will estimate the total in the population using one of two ways. If we know the domain indicator for every element in the population, then I'm going to know n, capital N sub d. I also know y bar d because that's my b hat. So this is a way to estimate. Basically, the b hat is telling you it's per unit y the value of y per unit in the subdomain multiplied by the number of units in the subdomain gives you an estimate of the total outcome variable of interest in that domain. So, but if we don't have n sub d, in other words, we don't have the indicator for everybody in the population, we certainly will be able to identify them in the sample by asking survey questions, for example. We'll be forced to use the capital N, which we do know from the sampling design, and then this U bar. Now, U bar is an estimate of the average Y value per element in the domain, but it also kind of reflects the percentage of people that are in the domain because you're zeroing out some of those values, but you're multiplying this by the entire population. So essentially, this is the per domain Y contribution in the population per domain element. And so this is kind of like a rate of Y to domain. When you multiply this by the entire population, this essentially gives you a total, an estimated total on the Y variable for just the domain of interest. This is not as powerful of an estimator, obviously, as this one, because this uses additional information. We have to essentially estimate that from our U bar. And remember, U bar is the numerator of B hat in this case. So now in this situation, if we're in this situation where we don't know n sub d, we're going to have to calculate the standard error of this statistic here. Now, if we do know n sub d, the standard error of this is nothing more than nd squared times the variance of this estimator. Let's write it down again here. The variance of t hat ud, which is the variance of nd y bar d, is nd squared times the variance of y bar d. This we know, assumedly, if we know it. So it's a constant. It comes out of the variance calculation. And the variance of y bar d is what we just saw above. So we already know these formulas. But if we're in this scenario where we don't know the domain variable for the population of interest, we're going to estimate the variance of this estimator as n squared times the variance of u bar. And the standard error of u bar is going to be, or the standard error of the t hat is n times the standard error of u bar, and this effectively is coming from simple random sample using the formulas that we had from chapter 2, and this s squared u is now going to be the sample variance across your entire sample. We're including everybody in the sample, so there are n elements here that I'm actually taking these square differences of, and the u bar is the overall average for those elements that have been zeroed out and those elements that haven't been zeroed out. So essentially what we're trying to get is the per subdomain contribution of the y variable per population element. And then when we multiply that average by the number of population elements, we should get the total number of contributions for the subdomain. That's kind of what is going on here mathematically. Now this is nothing more than the sample variance of the ui's from your entire sample. Now clearly there will be likely more ui's than there will be yi's in this formula here. So the summand here is actually coming up across n sub d elements, which is likely going to be smaller than n elements from your original sample. Now it's possible that you take a sample and everybody in your sample is female or in the domain of interest, for example. So in that case, it could be the same. But in general, this is actually picking out the y variables and staying on the y scale, which doesn't zero anyone out. It only focuses on those items that are in the subdomain. This one actually does all of them. It takes the y values and subtracts from it the y bar or the u bar. So again, this is not ui, but it's actually the yi variables there. So now let's look at a couple of examples. I'm back now with a clarification. The s squared u is actually the sample variance of the ui's in the entire sample, which is exactly correct. But in the notation, I had yi here, and it's actually ui. So please make a note of that. We're actually on the u scale now, where we've multiplied each y variable times the indicator of whether or not it's included in the domain of interest. So some of these ui's are actually going to be 0. Others of them are actually going to equal yi for the elements that are in the domain. So don't let that confuse you. There was a copy and paste error here. Now it is fixed in the notes. I'm going to look at a couple of examples with you. We're going to walk through them with Excel, and I'm going to show you how I set up these problems, which is exactly how the software in R does it, but at least it's helpful to kind of go through step by step to see how these things actually work, because then you can actually track what is contributing to each of these estimates. We want to estimate the average education level in years of education for those members of our Falcon Villas who voted in the 2000 election. We want to estimate the total net worth of these residents in terms of their income for a point estimate in a standard error. And for the last part, we want to assume that we don't know that n sub d is equal to 13, and then assume that you do know it. So our outcomes of interest here are a few things. We want the average education level for those who voted in 2000. So our domain of interest for this variable is vote in 2000. We also want total income for voters in 2000. And so the domain, so we have two things that we're looking for. We're looking for the average education level, and we're looking for the total income across those members in the Falcon Villas who actually reported voting in the 2000 election. So our outcomes of interest are clear. Our domain of interest, again, is the voters in 2000 election. We're going to use a simple random sample of size 10 taken without replacement for our estimate. So before we do this, let's figure out our sample. So you can find this sample file in example 4.9.xlsx in the datasets folder, as well as in the course notes folder. And so this is just the sample that I drew. It's a 10 element sample. You can see here that this is a lot of the information from the Falcon Villas. And now this is the education level that we care about. And this is whether you voted in the 2000 election. And you'll notice that I sorted the sample here so it's easier to compute these things. And you'll notice that my xi is just going to be a 0 if you're not in the domain. So that means if you didn't vote in the 2000 election, you're going to be a 0. If you did vote in the 2000 election, you're going to be a 1. Because the voted variable is already a 0, 1 variable, and because my domain of interest completely aligns with this variable, effectively my xi variable is simply the voted 2000 variable. There's no illusion here that these are the same. It's just I'm trying to call this out and walk through the steps with you so when we go forward, because in some cases we'll need to identify the x variable in the software, and the x variable may be a complicated combination of other variables. So in any case, in this case, it's a pretty simple scenario. The UI variable is going to equal the xi times the education. So if I take education and multiply by this value, I'm going to get the UI. So every time I have a 0 for x, I'm going to get a 0 for UI, which we know already. Every time you get a 1 for x, we're going to basically get the education value for that particular sampled unit. Now, my y bar hats of UD is effectively going to be the U bar, so the average of these elements here, divided by the X bar, and that was going to give me 16 1/3. And then my S squared YD is the sample variance of only the non-zero elements here, and that is going to be given here. So now my estimate of the, so you can see here that U bar is 9.8, X bar is 0.6. If I take the quotient of these things, I will get the 16 1/3. Another way you could express Y bar hat UD is the sum of these elements divided by the sum of these elements, because the little n's cancel out in the U bar over X bar equation. But in any case, that's how you would operationalize it. This S squared YD is the basis of the standard error, again, for my B hat estimate, which is the same thing as Y bar hat. And so in this case, we would estimate that the average years of education for members in Falcon Villas who voted in 2000 is about 16 1/3 years. Now, we've calculated this. The standard error of the estimate, again, is going to use this formula. We already saw this S squared YD, which again is just the sample variance of these non-zero numbers in the U column. So let's fill in some gaps here. We took a sample of size 10. There were 24 members in the population. There are 6 people who are in our subdomain out of the 10 that we sampled. We can see that very quickly by counting up the x's that are actually 1. And so we'll keep going with the formula. The sample size was 10. Again, the number in the domain is 6 minus 1. The variance of the y elements in the domain in my sample was computed to be 17.06667, and then the overall sample size again was 10. So the variance is 1.239. Now the standard error will just be the square root of that. Now let's continue with the estimated total income for all of the people who voted in 2000. So we want to estimate the total net worth. Here, yi is the income variable. Xi is whether or not you voted in the 2000 election, which was just like we had before. And first, we're going to assume that we know this n sub d because we're going to use our y bar d that we've already computed. And the number of folks is the number of folks who voted in the 2000 election from the population. And so our t hat ud is going to be this capital N sub d multiplied by the y bar d, or the b hat, if you will. And the standard error of this is going to be n sub d multiplied by the standard error in y bar d. We've computed both y bar d and the standard error of y bar d already in the first part of this example, so we should be able to do this pretty easily now. So here is the idea for the income variable. So again, the xi's are going to be 1 if you voted in the 2000 election. The ui's are going to be equal to the income if you had voted in the 2000 election. So my s squared yd is, I made a mistake here. We have not already computed y bar d, and we haven't computed the standard error because that was on the education variable. So we're moving now to income. So pardon me for that. Too many videos in too short of a time. It's all running together now. So pardon me. So in this case, we're going to see a same setup. So effectively, you've seen this once already. This is exactly the same way that I would approach this problem in doing these calculations by hand. A couple of things to note here, though. We're going to need each of these quantities because we're going to assume that we either have y bar d or we don't. And so the idea is, if we look at the s squared yd is the sample variance among the non-zero elements, and s squared u is the sample variance among all elements. And you'll notice that the s squared u is larger than s squared yd. We pay a penalty for not knowing the n sub d. And essentially, because any time that you have a variable that's on the magnitude of income, and you're zeroing out portions and you're taking the variance of all of these, the variance balloons because you're talking about the range is increasing considerably. And so you're seeing a very large increase there. So our y bar hat sub ud is going to be the u bar divided by the of x bar. So, and again, that is what you are seeing here. And so you will see that this y bar hat is 41,462. The standard error of y bar is, and again, the averages are here. So this is actually a typo, this 6115. It shouldn't be there. Let me fix that really quickly for us all, so that's not confusing. All right, that should do it. Okay, so again, the averages for these, so y bar u is 24,000 and change, and x bar u is 0.6. If I take the ratio of those two things, I'm going to get the b hat, or the y bar hat ud in this case. And the standard error is going to be from the equation. I'm going to take, I have 10 elements in my sample, 6 of them satisfy the subdomain. I've got s squared yd of this value here. Again, my sample size was 10. The overall standard error was 2569.03, and that's the standard error of y bar hat. Now, to finish, I'm going to calculate, so this information is carried over from the previous page. Now, if I assume that I know nd is 13, my t hat is simply 13 times y bar hat, which is exactly how I got this number here. So this 53,000 is 13 multiplied by the y bar hat. and the standard error is the standard error here multiplied by 13, which is exactly what you get here. If I assume that I don't know what ND is, I'm going to use n equals 24, and my t hat is going to be 24 multiplied by u bar. So I take the 24 times the 24,000, and I'm going to get something like 597,062. The standard error is going to be the 24 multiplied by the standard error of the 24 multiplied by the standard error that we get from using the S squared U's and the FPC essentially. And that calculation is going to be here. So again, the standard error of t hat UD, where I don't know ND, is going to be n times square root and so I use n is 24. I have a sample size of 10, and then this S squared E is, S squared U, sorry, the wrong notation. The S squared U value is what we see here, this 4 million and change here, 499 million. And so that is going to equate to the standard error. Now you'll notice that the standard error is about 4 times the size of what we'd get when we know the population size of our subdomain. So this is the idea behind knowing the information can actually be really useful at reducing the standard errors of our estimates. And again, these are all of the calculations that I've just written out for you. They're there for your reference in case you missed any of the calculations on your own. I'm going to ask you to do this example 4.10 at home. Essentially, it's exactly the same, except this time we are using the same sample, but we want to estimate the average gas mileage for trucks that are owned in the Falcon Village population. So we have a miles per gallon variable, but we only want to look at it for the trucks. And the car type equals T indicates truck. So in this case, you'll see the math already worked out. These solutions are already provided for you. And so I'd like you to work on this one on your own. For next time, you can bring questions to our regular meetings, etc. Again, this sample is provided for you in the example 4.10.xlsx file, so you can set it up yourself as well. Okay, thank you all for watching, and we'll see you next time.